So in this video, I want to show you how to write another test bench. And what I did is I selected the modular M counter and I wanted to write another test bench for it. So I started all the files, I added the test bench already. So let's get started. So what we usually do is I do the declarations of everything I need to do. For example, here I have a local parameter and that's M, and I'm just going to give it the value 10. That's fine. And I have another local parameter since I'm dealing with sequential circuits. I'm doing basically, this is the clock period, okay? Clock period, okay, that's fine. And then you can basically tell me, well, I need a logic clock, I need a logic reset, and also I need a logic, for example, n minus 1 to 0 q, but I don't have a n because I didn't calculate it, but we know from the code itself that n is just basically the c log 2 of m. So we're going to do that in here, and we're going to do this. Oops. Okay, so let me just write that c, and it's a system function, so it's a ceiling of log 2 of m. Okay, that's fine. And then we're going to have this, well, we're going to have an output. It's not an output, but we're just basically say logic max tick. Okay, so that's good. We did that, and then we need to instantiate the unit under test. So it's as simple as saying mod m underscore counter, and then we're going to say, well, okay, so dot m, I'm going to pass it the value m, and then unit under test is 0, and basically dot star, so match every name by itself. Okay, and here we generate the test vectors, and we know how to write the clock, for example, and I will generate a clock, and the period is going to be 20 nanoseconds because I will be using that t, and it's using the always. I'm going to do begin and an end. And what I will do is I'll set the clock, and this time I'm gonna set it to 0 initially. You can set it to 0 or 1, it's up to you. I'll set it to 0 initially, and then I'm gonna do this here, t divided by 2, and then the clock will actually flip to 1, and then t if divided by 2, and that's pretty much it for the clock. Do I have a reset here? Of course I do, so I'm gonna do that here. It's a sequential circuits usually have resets. Okay, initial, okay. Reset. Okay, so we're going to do the initial, I will say begin, end, and what I will do is I will set the reset to be 1, a binary 1 for a certain period of time, for example, till maybe half a clock cycle, or yeah, neg edge clock, and then here we do reset and we say equals 1, be 0. Okay, that's fair now, and then what I need to do is I need to generate the stimuli to actually stimulate all the inputs. Oh, wait a minute, this is just a modular counter. All it takes is actually the m as a parameter. Let me take a look at this code. It just takes an m as a parameter, it takes a clock as an input, and it takes the reset as an input. The rest of it are outputs I'm just viewing. So all I have to do is just run it. There are actually no vectors to generate, and that's totally fine. So I'm going to save this here. I will run the simulation in here, and then usually I'd like to see it at the very bottom in here, and that's fine. Do this that way. Alright, so that we get to see all the signals. So let's do this here, and what you can see in here is I do have that, and I'm starting this time the clock, I'm starting it with a 0, and then every 10 nanoseconds is switching, so my clock is okay, and my reset is running to at 1 till the first negative edge of the clock, which is here. That's also fine. It's setting me to q equals 0, and that's okay. And then of course, because it's a modular counter, if you remember the functionality of that modular counter, it will, and since m is actually set to 10, meaning it's actually doing a 10 count from 0 to 9, you can see it's going from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it resets to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These two are parameters I can delete. They don't change. Okay, so you can delete them here. All right, good. So now let's take a look at the max tick. Well, the max tick only operates whenever the value of the timer is at 9. So this is here, this is here, this is here, this is here. And this is why modular counters are used as timers, because if you think about it, well, I'm counting from 0 to 9, so I'm counting 10, and it takes me, in order for me to count 10 counts, I need 20 nanoseconds, because that's the period of the clock, because I'm always increasing that counter. So 20 times 10, okay, it's actually 200 nanoseconds. So let's see, if I actually stop in here, that's 190 plus 200, you're gonna get 390 plus 200, you're gonna get 590 plus 200, you're going to get 790. So these ticks are actually calculated to the nanosecond, and these are why these modular counters are actually used as timers. So a lot of the times you're going to see that this queue is not really necessary. You might not need it. So all you have to do is just go in here and, for example, change that queue and put them, for example, in here. Instead of having them as output, just create them as a logic. Nothing will change. It's just you're not exposing it to the outside world. And of course, if you do this, you're going to have to go back to your test bench and just remove that queue, because it's not a signal anymore. It's not available to you. It's not part of the inputs and the output. You run the simulation and you're going to see, yes, we're going to discard everything. That's fine. Okay, so you're going to see that in here, and you can see, I can also see the parameters which I can delete. Okay, and you can see that's what I care about in here. What I care about is that tick here, and it's actually ticking exactly what I want it to be.